I'm going to just give you a very quick overview of string solving, assuming that assuming very little on you here. To start with, what are string solving? Well, they're simply solvers for satisfiability modulo theory over strings. That means that the domain is the set of all words over some finite alphabet, and the set of all the operations, the string operations, are things like concatenations, regular expression matching, length constraints, replace all string transductions, etc. So we can, for example, have a formula like this. Says that S2 is a concatenation of S1 by S1, and the length of S2 is equal to the length of some other strings, S7, etc. Right? Okay. So of course, just as for integer domains, different combination of operations gives rise to different theory over strings. There are really a lot of string solvers to list here, and at the risk of offending some people in the audience, I will still list them anyway. So there are so many of them, really. I mean, I just don't have enough space in my slides. So you might ask, like, why you develop string solvers? There are several main motivations for that. The first one is, the most common one is static analysis of security vulnerabilities in web applications against code injection, NXSS, cross-site scripting. So this is basically caused by improper handling of untrusted strings. There are also some other reasons, like automatic test case generation for scripting languages, and also maybe something that might not be so common, not commonly heard of, is also that this is also commonly used in graph databases. If you look at path query languages for graph databases, they're also, you can think of them as some kind of string logic. Okay. So string solving theory and practice. There's really, string solvers get faster and faster every year. Yeah, so the heuristics get faster and faster every year, but there's much less progress on the theory side. What do I mean by that? I'm mainly referring to the foundational issue of decidability. So what are known to be decidable? Well, let's start with the most classical result here that everybody cites, Makhanin's results, that word equations, basically these are just strings logic with only concatenation operator. That is decidable. So you can express things like that, all right? So it actually is only just a single equation, all right? So Buchi and Zenger, I think I'm citing the journal version. So in the 90s, they proved that the general existential theory over strings with concatenation can be reduced to just one single equation like that, all right? So you can, for example, write something like this. And here is also an observation by Schulz in the 90s that you can also get decidability with regular expression matching. Okay, so for example, you can say something like this, and plus S1 matches this regular expression. Okay. Well, so that's these are all before the 90s, and this open problem is still around for 25 years apparently, right? So. What about word equations with length constraints, for example? That's been around for a long time and nobody has solved it. Okay. And there are also a lot of evidence that if you want to analyze XSS, you'd better be able to express some kind of length constraints. Okay. Now, in this talk, I'm even gonna propose something further that. Concatenation and length constraints are not enough. You actually need something more, which is string transductions. And I'll explain to you what I mean in a minute. So just before that, I'm going to recall, let's just talk a little bit about cross-site scripting, just for those of you who might not know what it is. Okay, so here is Dilbert. He's a good guy, and he just received a friend request from, so he's using some kind of social networking application. Okay, he just received a friend request from the evil cat. Okay, and the evil cat basically he created a user profile with this name. Okay, and then he sent a friend request to Dilbert. And then somehow on the page that Dilbert downloaded, so suppose he uses Firefox, yes, for an argument's sake, there's this statement here. All right. So the effect of this thing, the effect of this statement is actually inserting this kind of this string into the HTML of Dilbert, which actually caused Dilbert's web browser to go into this evil site. Okay, so this is an example of XSS. All right, so basically the idea here is that this string has not been properly sanitized. Okay, so this is what people do when they deal with HTML5 and JavaScript. They have to sanitize the input data, right? So by that I mean you escape certain characters. For example, in the case of script, you can, for example, do something like this. Every occurrence of less than, you replace it by this, okay? The HTML character, the HTML entity of that, and HTML entity name of that, and also greater than, you also replace it with this, okay? So this is kind of replace all operation. So you replace every occurrence of the string in the word, sorry, of the character in the string. Okay. So if you want to add sanitization, so you get you basically get a code that looks something like that on Dilbert's browser, right? So this is basically I'm just assuming some Google Closure function here that does this kind of escaping. It's called HTML escape. So for example, here's an example. If you have this, then it will be converted. So if x is this, if friend name is this, x will be converted. X will be this basically. Okay. And this script won't be executed by Dilbert's browser if you do it like that. So okay, so that's fine, but actually in reality the examples are much more tricky. So here's an example that I just adapted from Kern's paper from CACM 2014. Well, suppose the code in Dilbert's browser looks like this. All right, so this already does some kind of sanitization. So there are actually two sanitization functions here. So first you have an HTML escape, which we saw just now. So it converts a character to the HTML entity. Okay. So certain meta characters, reserved meta characters like less than, also n goes to an ampersand. Okay. So and then here you have another one here, the JavaScript escape. So this is the what is commonly called the / escape. Yeah. So you, for example, so some certain meta characters like this will be replaced by this. Okay. So or this thing. Yeah. The / escape. And also, if you have double quote as well, you also replace it by that. So here's a question: is this code vulnerable to XSS? It's not that easy to see, right? But I mean, apparently, even after you have this sanitization, it's actually still vulnerable to XSS, and I'll show you in a minute. So this is the code again. So let's just start with the innocuous input. Yeah. So for example, Tom and Jerry. Yeah. So if you use this in name, then you get this will build the HTML element, this HTML element, right? So it's pretty innocuous. Nothing will happen. So let's start with another one. Let's see if you do this. So this looks really weird, but you can synthesize that, and then you get what do you get? It look like this. Right. Can everybody see that? It's a little too small, maybe, but is that all right? Can you guys see that? Yeah. All right. So so this looks fine from just by looks fine at a glance, but it turns out what happens is that there's something evil going on here with inner HTML. So this inner HTML, if you actually run on most browsers, so this will mutate the strings here into this thing. So this thing will be converted back to the original character, right? So that's actually an XSS. So what will happen is that this will just pop up. You'll have a pop-up window alert1. Of course, you can replace alert1 with something evil like window open, something evil. So that will also work too. Okay. So what's the moral of this story? Actually, well, I mean, XSS is kind of tricky, but the thing is, like, what really happens here is that the programmer wrote something that actually that is fine. He actually applied the right sanitization functions, but he actually applied it in the wrong order. That's all. That's the only problem here. Okay. All right. So if you want to detect XSS via string solver, so I'm just going to show you several steps that people usually say. Yeah. So what you'll do is that first step, you identify the sync variables. So basically, these are like, if you see inner HTML or document write, then you identify the sync, identify that as a sync point. Okay, and then you find the next thing is you find attack patterns from known vulnerabilities. Like, there are many documented ones from Open Web. What does it stand for again? Open Web Application Security Project. Yeah. So for example, in this case, you might, for example, want to come up with this. This looks ugly, but let me just say what it means. This basically means that you have you have this in this one-click attribute, you have view person function followed by something else. Okay, so that's basically what it means. The third step is to express the program logic in a string logic, which, for example, looks like this: concatenation of these 5 constraints. So here is like X is R1 name. So basically, you apply some kind of string transaction to name, and then so basically, I'm just following this thing, right? So in the X, you apply the second one here, escape string. You apply that to X, you get Y, and then Z here will just be this will correspond to the this thing here, the thing on the right here. Okay, so it's a concatenation of this thing, and finally, you have another one here, R3, which does the string transaction for the inner HTML mutation. Okay, and finally, of course, you have the fifth constraint, which is that this thing, the final variable has to match the attack pattern. Okay, so it looks kind of like that. And then finally, you check for satisfiability. If it's unsatisfiable, then it's all right. If it's satisfiable, then there might be a problem. Okay, and then there are ways to make it more precise if you get satisfiability. But I'm not going to talk about it. All right. Okay. So which string logic? So here I flesh out the constraints again. So you have concatenation, but also here you have this R1, R2, R3, which is a kind of replace all kind of operations that we saw. These are basically just string transactions. So let me explain what I mean by string transaction on the next slide. Oops, sorry. Okay. So final state. These are basically. Okay, so at least for the purpose of this talk, what I'm going to talk about is finite state input output transducers. Okay, so what are these? These are basically just finite state automaton, but the transition label is a pair of words. Okay, so V and W here. So here's an example of a finite state transducer that just erases every occurrence of 1. Okay, so you see that 0 is mapped to 0, and 1 is, you get rid of 1. So here's another example of finite state input output transducer that replaces some reserved characters by the HTML entity names. So for example, here greater than is replaced by this. Actually, this is a typo here, so it's supposed to be GT. And less than is replaced by that, and then and here is replaced by the n percent. Okay. And the relation that is recognized by the transducer is simply the set of input-output pairs that are recognized by the transducers. Okay, so Q0 here is the initial state, and Qn here, and F here is the set of final states. All right. So there have been a lot of works modeling this, sanitization functions and implicit browser transactions like inner HTML, document write, as finite state transducers or extensions of them. So I'm just going to list only a number of articles. So one of them is by a friend of mine at the same university, National University of Singapore, Pratik Saxena, and also I think Boris as well, obviously. So Yeah. So the main question that we have here is theory of strings with concatenation and finite state transactions decidable? Okay. Unfortunately, the problem is not decidable. So I'm just gonna actually show this very simple formula. Logical formula. Yeah. So x equals y concatenate with z, and x equals you apply a transducer R onto Z, and that's already undecidable. Something very, very simple like this already undecidable. Actually, you can even make it even simpler. You can only just use erasing transducers. Yeah, that's already undecidable. So there's a lot of things that are undecidable here. So what can we do about that? So in this paper, what we managed to show is that the straight line fragment, that is, you can also think of it as the SSA form of a string logic program, is decidable. So I'm going to show you what I mean by that. So the definition is very simple. So you can have an empty set of conjuncts. Okay, so that's in this straight line. So if you have something that is straight line with variable x1 up to xm, then you can add another conjunct, which is with a new fresh variable with this assignment xm plus 1 equals something on the right, okay, pm plus 1, such that this pm plus 1 is basically either a transducer or a concatenation, such that the y's here, yeah, are variables that are already in S or new variables, okay? So that's basically the definition. And you have, you can also add regular matching, so just Boolean combinations of expressions like that, where L is a regular expression. So what we show is that this kind of this logic is decidable, and in fact, it's decidable in exponential space. So in fact, actually, this is exponential space complete. Okay, so and we have a bounded model property, which is that every satisfiable constraint in SL has a solution of double exponential size. Okay, so you can think of the last theorem here as some kind of it's a kind of completeness guarantee for several existing string solvers. There are string solvers out there that support both concatenation and some kind of transactions like replace all. So this, you can think of it as a way of providing completeness guarantee. And actually, as a matter of fact, under reasonable assumption, we can get a much better bound, single exponential bound. I'll explain in a minute. So how much time do I have? Okay. Okay, so, all right, so I'm just going to say very quickly. So the proof idea here is that, so for any formula, you just remove the concatenation from the formula. That's all. Okay, so that's what you want to do. And in order to do that, if you see this example here, what you would do is that, let's say that R here is a transducer that has states Q0 up to Qn. Then basically what you do is that you compute the following formula. Okay, so you introduce two fresh variables, y1 and y2. And then you divide this thing here into a Boolean combination of formulas that have no concatenation. Basically, the idea here is you have this Q0 and Qj here is that you try to guess the middle point where this thing, the concatenation operator occurs. Okay. And okay, so that's really the entire idea here. But the problem with this is that, of course, you can get something. So, if, for example, if you have a formula like this, y1 equals y0, y0, y2 equals y1, y1, etc., then the resulting formula uses, this many variables. As a matter of fact, it's exponential in the number of, in the size of the formula here. Okay. So you can use this trick to encode the exponential space Turing machine. And so solving the final formula is quite simple. So it's this is acyclic. So, and it is known that satisfiability for this kind of formula is decidable. And basically it uses the fact that just the post and pre images of regular languages under finite state transactions are regular. Okay. Just talking about improving the bound, actually, so I will just say something very, very quick here, which is that the doubling tricks are artificial in general, and in general, this kind of, the bound, there's actually this height here of the doubling tricks is actually very small in practice. All the examples that we've seen so far are, in practice, it's only 4. In this case, we get Okay, so there's no time for this, but we also can add integer constraints and still be decidable. Okay, so conclusion and future work. So we've argued that concatenation and string transductions are both important for access applications, and that we have straight line fragment of string logic with concatenation and transductions that are decidable, and even with integer constraints as well. So there are 3 future work here, but maybe I'll just ask you to ask me during the question time. So, thank you.
Sumesh, Chartered University, Wisconsin. So did you try putting some restrictions on the transducers itself to get better results? For example, all the XSS examples that you have had only bounded number of substitutions, so to speak, right? So like only few characters were changed by the transducer. Does it lead to any good complexity results?
So yeah, so if you look at something like HTML escape, stuff like that, right? So there's actually the list of characters that you can replace actually quite a lot. So all of these things. So there's, yeah, I don't think that's a good idea to do that. I mean, like, I guess in practice it's finite, but I guess, you know, if you have decidability for that, it'll also be like quite huge as well, right?
Another way of banning the Doman trick would be to person have linearity constraint. A variable can only be used once.
Yeah. Like you mean like once in the entire formula, or?
Yeah.
That's very, very weak, I guess, right?
Well, or perhaps once per constraint.
Yeah, sure. That's You can do that. Sure.
And then what happens?
In that case, you'll get just. Right. Okay. Yeah. Sure. So Tom Rath's question is, what happens when you when every variable only occurs once on the right hand side of an assignment? Okay. So what happens in that case? Because in that case, the doubling trick won't work, and you'll just get polynomial space complexity. So everything will just be you will not get this exponential space thing. That's what happens.
And is that class useful in practice?
I've seen a number of examples where the variable occurs like 3 times or something like that, and actually in examples in benchmark, so that I've seen. So I guess it's a good idea to actually allow a more general constraint. Yeah.
But I guess in this case, you just decompose the transducers away and just get assignments.
Yeah. So in that case, yeah. You mean like when only one of them? Yeah. Sure. Yeah.
So I have a question.
Okay.
So the Lawrence and Collin, University of Wisconsin.
Yes.
So you said you want to solve for SMP, and when I think string in SMP, this is not what comes to my mind. Because when I think arrays in SMP, it's not arrays over ABC or any kind of other. It's arrays over another SMP here.
Okay.
Why string over just essentially just finite alphabet or any very specific theory that is versus being strings any other like tends to be made into
Something more general. I guess like the way I was thinking about it is more like just like strings, as in strings. You know, like I mean, like I sort of compare it with something like integer arithmetic. You know? I mean, like people also call that SMT, right? So I guess that's the way I think about it. But I do get your point. I mean, like I think like people who study symbolic automata, they actually do something that is more general, and I think that's a good idea in general in
well,
practice.
because for the example you said that you have too many characters. In practice, when you have too many characters symbolically, you use the theorem of vector and
Yeah.
but,
I mean, I do agree. Actually, this. Okay, so it's disappeared, so it's actually question 2 of the future work too. So I think it's important to be able to handle something more general because I think like in general, in the worst case, you get some exponential blob anyway. So if you do that, right? So, okay, thank you. Thank you.